Okay, so I think we can get started. So firstly, thank you everybody for joining this webinar. Good afternoon, good evening, greetings of the day to all the participants from wherever you're joining, different geography. So let me quickly start, with the introduction. Myself, Sadaf. I work as an account manager in Detroit Engineered Products. And in this webinar, I will have Arjun, who is our project manager. He will be driving the main topics of the webinar today, supported by Kavin, part of Arjun's team. Okay. I hope my audio is clear. If any problem with my audio, somebody from the DEP team can raise the hand. Okay, so before I deep dive into the webinar topics, okay, I just want to quickly talk about the agenda first. Okay, so this is the agenda we are going to talk about today. Introduction in short, we already covered. I'm going to talk about DEP as a company, what we do, what are the services we offer. I will try to finish this DEP overview in next 7 to 8 minutes, and then I will hand over this call, to Arjun, who will talk about the listed webinar topics in battery applications. And then, most importantly, we will talk about our value additions, what makes us different from the other companies, competitors in the market. And the last 5 minutes, we will reserve it for Q&A. But in case if you have any questions in between, you can drop your questions in the chat, and we will pick those questions during the Q&A. Okay, so with that said, let me start with the company overview. So DEP stands for Detroit Engineered Products. We are a 25-year-old company. We started in 1998 as a software company. You might have heard about CAE software like HyperMesh, ANSA. So DEP has its own CAE software called Meshworks. As of today, we have 4 business units, as you can see: engineering consulting, where we do all type of turnkey engagements and ODC engagements for design and engineering. So all the way from design and CAE, all the engagements related to battery applications, automotive, non-automotive, control systems, embedded systems, software development comes under this division. Secondly, we have our software division. As I mentioned, we have our own CAE software called Meshworks. We sell this software to customers, and we also deploy it at their locations. And then in product development, where we support companies in a lot of innovative products. Okay, we have developed a couple of hardware products like drones, IC sensor, which are used for thermal runaway predictions, EV scooter. So a lot of product development initiatives, we do in product development divisions. Okay, and then in talent acquisition, we place people on contract. If you need any battery engineer, thermal engineer, software engineers, or embedded engineers for short-term, long-term contracts, we provide those engineers at the customer locations globally. Currently, we supply these type of resources, okay, to many OEMs and Tier 1 suppliers. When it comes to our global team, we are headquartered in Troy, Michigan. We have offices in California, Brazil, 2 offices in India, Chennai and Bangalore. They are serving as our low-cost design and engineering centers. Additionally, we have offices in Tokyo, Japan, and Shanghai, China. So whatever the locations in red on the map, what you see, those are our own offices, and all the blue font locations such as Germany, Italy, Poland, France, we work with our partners. So these partners sell our softwares and services in these geographies. And industry-wise, we support a wide range of verticals, but our primary focus is on automotive, which is responsible for 70 to 80% of our revenue. But we also are engaged with some other customers, in aerospace, consumer electronics, biomedical, heavy engineering. So we support all the engineering verticals. And globally, we are 550 plus team members. We are still growing year-on-year basis. Out of this, I would say 65% are dedicated to engineering and design, and handling a lot of turnkey projects, ODC engagements for customers, as I mentioned earlier. And around 20-25% are on the software side. Okay, so making a good mix of mechanical, electrical, electronics, and software engineers. And from these 550 team members, we have got 20%. They hold PhDs, specializing in areas such as CFD, high computing thermal analysis. As we know, battery being a specialized area, we need a very niche level of expertise here. And approximately 70% have got masters, and 10%, they have bachelors. So when it comes to services, we are a one-stop service provider for our customers. We can assist you from product ideation to creating a concept for your product, detailed design engineering, and all kinds of system engineering and mechatronic support. We have capabilities in developing control systems, whether it is engine control, powertrain control, chassis control, infotainment, software integration. We also support benchmarking for any of your competitive products. Okay, we have a dedicated lab at our Troy office, especially for benchmarking. So here we tear down the components. Okay, I mean we can scan the components no matter how big or small. From the scan data, we can generate a 3D model, and from the 3D model, we can perform all the CA simulations. Okay, performance simulations and testing as well. Okay, and we are also heavily involved in lightweighting and optimization projects. Okay, such as value engineering projects where customer asks us to optimize their design to achieve weight reduction or alternate part design. Okay, without compromising the performance. So all the way, I would say, from stamp structures, BIW, aluminum castings, plastics, interior, exterior, we have very good experience. Okay, so as you can see, this slide pretty much talks about the wide range of services. So we can proudly say that we could be your one-stop service provider for any of your design and engineering needs. Okay, you can count on us. And also in the EV area, we are very strong, as we know that the entire automotive world is shifting to electrification, and that is the reason we also invested heavily in this area. We can proudly say that we are working with almost every second or third EV company in North America. I cannot disclose their names due to all the NDA signed with them, but then here we provide very extensive support to all these EV companies. Okay, sometime it could be on component level, system level, or sometime for the entire vehicle, okay, including the BIW, chassis, powertrain, battery, control systems. So this slide talks about pretty much the depth of our services in the EV domain, showing how we can assist our customers either in designing an EV vehicle from the scratch or converting their IC vehicle to an EV vehicle. Okay, and we have all the way, we have capabilities all the way from, I would say, system level modeling, meeting all speed requirements, performance requirements using MATLAB Simulink, to designing the battery, determining the necessary battery size you will need, motor size you will need, and doing all kinds of battery simulations, okay, for cell level, module level, pack level, integrating that to the vehicle. And we also handle design and integration, for all the control systems, power electronics, wiring harness, both for high voltage and low voltage, whatever is associated with EVs. Okay, so this is a quick summary, of our capabilities in the EV sector. Okay, with that said, I would stop here. Okay, this was just a brief summary of DEP as a company, what we do, and I'm going to hand over the presentation to Arjun now, so that he could get started with the webinar topics. Okay. Over to you, Arjun.
Yeah, thank you, Sadaf. Let me share my screen. Please confirm when you're able to see my screen.
Yes.
Sadaf, you're able to see my screen, right? Yeah. Okay. Yeah. Thank you. Hello, everyone. I hope everybody's doing good, and thanks for joining this webinar. I am Arjun, CFD project manager from DEP. Today, we are going to talk about how the machine learning or machine learning techniques play a major role in the CFD and helps to ease our life in ease our work in day-to-day life. Be it is any industry, we do a lot of kind of analysis like NVH, crash and safety, CFD analysis. Why do we do this kind of analysis? Like if we are in the design phase, to know whether we are in the right direction, or if already the design is finished. So to validate this design with the benchmarking values. And also the major advantage of doing this CFD analysis is to reduce the prototypes. When I say reducing the prototype means our analysis has to be very much, results should be reliable, cost effective and time effective. All this can be achieved with the help of machine learning integrated with the CFD techniques and the CFD analysis. So yeah, being that said, as a brief introduction, I would like to jump into our today's webinar topic, advanced battery thermal and cooling system analysis using 1D CFD and mission-based techniques. This is the agenda for today. First we'll battery cooling and thermal performance using GT suite. We are going to see the thermal model as well as the cooling circuit model in the battery. And the main topic is like how we implement the machine-based technique in the e-motor cooling circuit of the complete e-motor. And then how we can implement the machine learning techniques in 3D CFD as well. And I'm going to demonstrate our inbuilt machine learning tool, which helps us to get the optimized design. So yeah, let's go to the first topic, that is 1D CFD cell single cell thermal model. The objective is to simulate the thermal performance of a single cell during the charging and discharging cycle, and also to monitor the SOC and the temperature. These are the, as you see, these are the assumption and boundary condition we considered for developing this model. These are the inputs like current versus time, and this is charging cycle and discharging cycle, and this is the single cell which is modeled in GT. These are the components considered for the modeling of the modeling in the GT. And this is discretization assumption. That is nothing but how we built the model in the GT suite. There are two ways to build the model in GT suite. That is by converting the 3D CAD model into the GT circuit using the Gem3D software, or else we can use the readily available templates in the GT suite to model this single cell battery. Here we have used some of the readily available templates in the GT suite. So let me explain. I have used the thermal masses here and electrical circuit over here. And this is the, as you see on the right side, this is the battery which we have converted in this into the GT model. And below you see this is the cooling circuit which has been connected to the thermal pad. So on the left is the electrical circuit. When the current passes to the electrical circuit over here, it generates the heat, how much heat is generated, and it is giving it to the thermal model here. And it is thermal model is giving the temperature feedback to the electrical model. This go back and forth until the cycle is completed. This is how, and also coolant will be flowing here. And this is how we get the final temperature over the period of the cycle, when we can observe how the temperature of the cell is varying with a particular charging and discharging cycle. So this is the result. This is the SOC of the battery over the cycle, and this is the battery temperature, which we can see here. The cell temperature we can see, which is within the limit. We see it is almost nearing between the 40 and 45. We consider usually the 50 as the higher target, should be less than 50, the cell temperatures. In this case, it is passing. Assume if it is not passing and going above 50 degrees Celsius, the cell temperatures. In that time, what we have to do, we have to optimize the coolant circuit, increase the flow rate, decrease the flow rate, or or we have to derate the current. There are certain many parameters we need to consider. So if we have to do it everything manually, then it takes a lot of time. Rerun, change one condition and rerun. It takes a lot of time and manual efforts. So this is where the need of machine learning comes into existence. Being said that, we will discuss about the implementation of machine learning in the upcoming slides. We will go to the next topic as of now, like 1D CFD battery cooling circuit discretization. We will see how the cooling circuit can be converted into a GT suite model. Here, objective is to convert this cooling circuit into the GT suite circuit. First, what we have to do is like we need to extract this coolant plate and the fluid core to be taken out, and then we have to take that coolant core to the Gem3D, and then we have to convert it into GT suite. Yeah. So here, these are the assumptions and boundary conditions we have used, and we have considered 20 liters per minute as the flow rate in this case, in this example. So once you do that extraction, and when you get the fluid core and convert it into GT suite model, as you can see on the right, this is the GT suite model. And we are mainly concentrating on the flow distribution on these branches 1, 2, 3, 4, 5, 6, 7, 8, as you see in the at the bottom. So once the cooling flow is 20 LPM is flowing through this, and we need to monitor how much flow is going through each branch here. That means each module which is going there. So after running this analysis, we'll get the results like this. The how much flow is going to first branch, second branch until 9, and this is the error percentage. So 1D will always get we will get after once we get the result, we'll always compare with the test results or as the 3D CFD results in or as any benchmark values. In this case, we got actually the 3D CFD results to compare with. So when you compare this with the 3D CFD result, there is a lot of errors we found here. So to overcome these errors, you need to tune it manually. There are some orifices here, the tuning parameters. You need to tune it manually to match it with the series of the results. This is after the results after matching with the, manually tuning, and it is matching with the 3D CFD results, and we have very less error when error percentage you can see here. So in the same way, the pressure drop of the overall system before tuning was this, and after tuning will be this. This is the 5% error bar, which is within the limit. I mean, in the range of 5% error bar. So in this case, when it is not matching, as you saw here, when it is not matching, you have to do all the tuning manually, and it takes a lot of efforts again, and it's again a tedious job, manual effort and time consuming. This is where again the need of machine learning occurs. Let me explain you another example, how to convert from 3D to 1D circuit. So this is the full engine, which you can see we are modeled in GT circuit. It's just a combination of conversion of CAD data into the GT circuit and also the readily available templates in the GT. So what we have done, we have taken shown an example how do we convert this exhaust manifold here into the GT jump 3D circuit over here. So we have converted this, taken this CAD model and then converted it using the Gem 3D and converted this and later converted into GT circuit and implemented in this overall engine model. This is just an example to show. There are many other parts we can do it in a similar way. So after doing this, we have built entire engine model in the GT suite, and we have run the analysis and compared the analysis with the dyno test results. And we were very well closely matching with the dyno test results with this one. Being said that, we'll move on to our main topic for today, optimization using ML approach. For this, I have taken the complete circuit of the E-motor. For our main motto here is to reduce the E-motor housing temperature by 5 degrees C. So this is the approach we have used, establish the 1D GT model of the existing cooling system and then generate the DOI runs and then establish the machine-based methods for significantly faster optimization time. And then we will get the big, once we establish the machine learning based model, we'll get the optimized feasible design and then verify that design and with runs again in the GT circuit. Okay, and then coolant flow rate, HTCs, heat exchanger tube line stack dimension. These are the some of the parameters chosen for the optimization. So this is the e-motor, e-motor. So this is we got this from the reverse engineering team. This e-motor was dismantled in our DEP lab, and from the reverse engineering team we got the CAD model. From there we converted that CAD model into the GT circuit, as you can see here. And these are some of the properties which we used. You can see over here. Okay. And then what happens next? This is the complete e-motor circuit. This is the main model you can see, and this is the coolant loop. I'm showing it separately. Whatever we have converted this motor into 1D circuit and showing each sub-assembly separately. This main and coolant loop, and this is the thermal model, and this is the e-motor. So e-motor is an electrical circuit. Okay. And then this is the input drive cycle, which we have used highway fuel efficiency drive cycle. We have used as an input, and we ran the analysis with the above set inputs, and we got the we got the housing temperature here. This housing temperature is almost near to 56 C. So we need to reduce this. This is our to 50. This is our target. And as you see here, the baseline time is 55.5 and the radiator outlet is 59. and these are the design variables and the values which we have used. Okay, and then goal is to reduce, as I said earlier, it is to reduce by 5 degrees Celsius. And then these are the design parameters like coolant flow rate, heat exchanger tube length, heat exchanger stack dimension, and heat transfer coefficients. This is the baseline values which is already present. This is the minimum value and maximum values up to which we can go. These values has been chosen based on our experience, past experience. Okay, and then coming to the next step is like in the GT suite, we create the DOEs, and this is the conventional process which everyone usually follows. DOEs, and then run the GT optimizer, and then get one finalized design iteration. But using the ML techniques, we feed this DOE generated from the GT suite to the eyesight DOE matrix, and then we create a neural network approximate function, or which is called RBF function, and then we run the optimizer to get the many optimized designs rather than one optimized design which GT gives us. So, and after getting that, we will finalize one design out of it. This is the new process, like implementing the machine learning via eyesight. And these are the design parameters as I explained in the earlier slide. I'm just highlighting in the circuit. This is the radiator, and this is the coolant flow, and this is the coolant jacket, heat exchanger. Yeah, these are the just highlighted which we saw in the previous slide. After considering all those things, we generated over 200 design of experiments table for all the parameters mentioned over here. Coolant flow rate, HTC, heat exchangers length, and heat exchangers width. After generating this DOE table using optimal Latin hypercube method in the GT, what we do is we export this 200 DOE to eyesight, and we feed it as in the eyesight optimizer. Eyesight optimizer develops a function using RBF model and the neural networks. And it without running the actual analysis, it generates the output. And this is the inputs we are feeding and outputs we are expecting from this one. Yeah. So here, after this setup, inputs and output setup, and feeding the DOE table into the eyesight for the using the RBF model. Next, we have to choose the generic algorithm, and we have to specify here the lower bound and the upper bound values, which we discussed in the earlier slides. The lower bound is the least values which it can go, and afterwards the maximum value which is going. The middle one is this one. So when we choose this genetic algorithm, and we are monitoring the motor housing temperature and the radiator temperature. So what it does is it runs the optimization in the background, and gives us the using without actually running the simulation, and gives us the optimized results. I mean optimized designs. So after running this, we got 11 optimized feasible designs over this, rather than GT. When compared, we'll get only one. Here we got 11 feasible designs, as you can see on the right side, and it has highlighted the most three feasible designs also, and given us this option for us. So what we did, we took all the three design options which is provided over 200 DOE table, and what we did, we ran again with those values in the GT suite, and we compared with the eyesight output. This is the eyesight output, you can see. This is the eyesight output, and we compared that with the GT suite output, and the error percentage is very minimal. That means we are in the right direction. The results what we are getting is the correct. This is for the motor housing, and this is for the radiator outlet. You can see the error percentage over here, which is very minimal and very much acceptable. And this gave actually the three designs for us to choose. So out of which you can see we ran all the three designs here. This is the baseline result and all the three design results, which is very much in the target which we wanted. And here also the similar way. And out of which it has given three designs. We chose design one, which is the lowest of all three, and design two, which is the lowest of all three here for this heat exchanger, and heat exchanger outlet, which is the lowest of all three. We took all these three designs and ran the simulation, and again we got the expected results. So this is how the implementation of machine learning techniques helps us to reduce our efforts and get the results very accurately, and we get multiple options and we can leave the options to the designer to choose. So conclusion is concluding this analysis, the model setup we did in GT Suite, and DOE creations also is been done in the GT Suite, and we have taken that into the RBF neural networks in the eyesight, and genetic optimization techniques has been used to get the multiple feasible designs. And most practical design, as I said, the lowest of all the three designs, we have taken it out and validated with the GT results. So this saying this ends the how I mean the demonstration on how the ML based techniques implemented with 1D. Now we can go and we will see the how ML based techniques is merged with the 3D, or how the ML based techniques helps in the 3D CFD analysis. So this is the thermal runaway analysis. Here the objective is to study how the, if say for example, if one cell is going for the thermal runaway and how it is propagating, affecting the other cells in the module or in the pack level. So here we model, what do you say, we consider all the parts and model it. And deliverables will be the critical component temperature, velocity, and pack pressure. So say for example, we have designed a part two for the exhaust. For example, one cell got into thermal runaway, and that vent gases is going out of the pack, and we have designed a part two for the going out of the pack. And we have designed a coolant circuit in a more efficient way to cool down this cell, say for example. So each and every time when we change the design, we have to mesh it and we have to run it in the 3D CFD. And again, it is very tedious job and it takes a lot of time. So here again, we can implement the machine learning techniques in order to reduce the timing and manual effort. Here is another example where we machine learning actually comes into requirement in the external aerodynamics. We all know that we do the external aerodynamics of the car analysis to calculate the coefficient of the drag. So here, say for example, again here, when the requirement is not met, we tend to change the design. Whether it might be a spoiler design, side fender design, rear fascia design, anything it might be for that. So for each and every change, again, it is the same similar process. Since this is a very huge model and it involves a more computational time, it is again more time consuming. And we have overcome this problem by developing our own ML based, machine learning tool, which helps us to get results very faster. Okay. This is the tool which we developed in house, and we have integrated this tool into the our tool called Meshworks, which Sadaf has already mentioned you in the earlier. So we developed the tool and integrated it to Meshworks, which is predicting the drag coefficient whenever we change any design specification with this one. So for this, what we have to do is just we need to bring the vehicle model and parameterize the design. For example, if we are wearing the spoiler, we need to parameterize the spoiler. And we are wearing the rear fascia, we need to parameterize the rear fascia. In this one, we have parameterized file and loaded into this ML based tool. So I have a video here to show how this ML based tool works. Okay, I'll play this video. Yeah, and I'll be explaining. This is the drag coefficient value, which you can see here, okay? And we are loading into the parameter. We went to the parameters here. As you can see here, the spoiler rate is the parameter, spoiler angle is the parameter, and this windjet angle is the parameter. And like this, we have many parameters here, okay? And we can easily see after varying each parameter how this drag coefficient is varying, and you can visualize these changes also in this one. Yeah. Now what we are doing here is first we are spoiler height here. If you observe here, we are varying the spoiler height. Okay. This is the one of the parameters, and we can see observe here how the drag coefficient is changing without running the analysis. This is the beauty of the machine learning tool which we have developed with in-house. So now we are trying to vary the different parameters. Earlier we varied the spoiler. Now we are varying here this zone. If you observe this zone, we are varying this zone and how the drag coefficient is changing. Yeah, and now we can vary the glass angle, side fascia, sorry, side fender. See, if you observe here, it is changing over here. This changing. This just a slide of bar we are doing, and we are getting the instant results of the drag coefficient over here. And this is the bottom side width. This is the side width we are varying with minimal. And now we are wearing the glass, rare glass. If you observe here, if you observe in this zone, the rare glass has been varied. So like this way, we can create as many parameters as we want, and we can play with these parameters. We are showing just an example in this zone. We can create it at the front fascia zone also. Yeah, it's left to the user, and it also depends on the requirement from the customer. Now we are varying this. Yeah, this is the end of the video. This is a small demonstration of how our machine learning tool works. Okay. And yeah, being said that, and this is the end of my presentation. Thank you for listening to me. And then before ending, I should mention that the key takeaways. So key takeaways from this is like that in the DEP, we are really capable of converting the complex real world problems into 1D system, and we can optimize that designs using our machine based approach, machine learning based approach. And this is a great cost and time reduction in the design process as well. And we have a dedicated machine learning team, and we develop the tools, and we develop the machine learning codes according to the customer requirements. Yeah, that's all I had for today. Thank you. And